for normal computers, because if you actually look back at the history of computer games, of games made with computers, when did that begin and why did people start doing it? And you find that one of the first examples were people going to trade shows with new technologies, wanting to show them off, and doing that by making simple games like tic-tac-toe. And also people making games like tic-tac-toe to see how humans and computers interact with each other, and other sort of basic things like that. So the main idea behind making games for computers in those early days was about education. It was about teaching people about the technology, and also about allowing people themselves to work out what this new technology is and what it can do for them by making games as a very simple application. Because a lot of people like to learn by doing, and sometimes when you don't have much knowledge, that you can't do anything big and sophisticated and fancy, but maybe you can do something fun, like making something like a very simple game. So this was the beginning of games for computers. They were quite simple. They were mostly done for education, either the person teaching themselves how to program by making the game, or teaching other people about programming by making the game. But as time went on, they became more sophisticated, and you got to examples like this on the PDP-1, which is called Space War, which actually turned out to be kind of like the prototype for some of the first arcade games. So even though it was made by some students who just wanted to try out a new device and teach themselves how to program it, it kick-started well, the kind of video game industry we know now. So this is the kind of context you have to keep in mind, mostly when you're thinking about games for quantum computers now. This is not making the next AAA game. It's not about making Fortnite or Minecraft or anything. It's more about if you are learning quantum computing and you want to have some sort of fun little way of applying any knowledge that you get, and you want to explore what you've learned and you want to try it out, then you can do that by making, well, you can do that in all sorts of ways, but one way, especially with a historical precedent, is to make simple games of it. Although, as I say, I am looking at some of the more practical applications, so what it might be actually useful for in the real world. So what people who actually make games might want from a quantum computer. And for that, I'm looking into procedural generation, which is a technique which involves lots of the kinds of algorithms that you learn about in textbooks, optimization and constraint satisfaction, in order to make content for games. But using those kinds of algorithms that you find in the textbooks is in any case a long-term thing at the moment. We need fault-tolerant quantum computers for that. So this is a long-term vision, but we can also try and push the boundaries and see what we can do with what we have now. And today I'm going to go for a very simple example of procedural generation, and one that you can actually do with just one qubit. So really it's a way when you are learning about one qubit to put your knowledge to the test and to learn more about it. Okay, so for this I'm going to be using Jupyter notebooks, and this is something that are quite useful for learning Python. And of course, quantum computing is quite Python based. And someone seems to be drawing on my screen. That's quite interesting. Yeah, so Jupyter notebooks are very useful. And we have, at IBM, we have this website, quantum-computing.ibm.com, that you can go, and it's free, and you sign up. And you can use Jupyter notebooks in a web-hosted way. I always find it easier to use them on my own computer, except that sometimes it's a pain to install them. So if you want to get away from that pain, then you can just use the ones that we've provided. You just click on where you come here to get notebooks, you click on New Notebook, and then you can do everything that I'm doing in this talk. And also what I'm going to be doing today is I'm going to be trying to live code some quantum games, but I've already sort of done the code that I hope to do. And you can find it here at gist.github.com/quantumgym. So if you want to follow along with the code, I suppose I should paste this list somewhere at some point. Sorry, this link. And if you go on here, quantum game, then this is basically the code I'm going to be going through today. But before then, I hope I need to click on the place where in the bar, well, maybe I'll just close a few tabs down because the Jupyter widget is in my way. Okay, so this is the beginning. This is where I'm going to start live coding stuff for you. I've already put a couple of things in here. So we're using Qiskit. There's a few frameworks of quantum computing that you can use to actually do programming with a quantum computer. One of them is Qiskit, and of course it's the best. I don't say that just because I work for IBM, but I work for IBM because Qiskit is the best. And so there we import a few things. Quantum circuit is the object that we can use to handle quantum circuits. Execute is a way that we use to run circuits in Qiskit. Air is what we use to, well, basically it contains all of our simulators. We're just going to be using simulators today. But if we wanted to use real devices, we would use IBM Q. And also we're going to use, I think we're going to use pi. That might be, and we're also going to use the floor function. So two things that we need numpy for, or numpy as some people call it. If you're being really consistent, it should surely be called numpy for numerical Python, but no one seems to do that. Anyway, so first I'm going to take you through the idea behind the first quantum game ever made. So back in 2017, we already had quantum devices online. We had quantum computers that we could access online. And so that was through IBM. And beginning in 2017, we also started to have these frameworks, these ways that you could programmatically use these quantum devices. Because before we were able to use them programmatically, you had to use sort of a graphical drag and drop interface, which was great. But also, if you want to do something programmatically, then it wasn't good enough for that. So as soon as we had devices and we had a way to programmatically address them, I realized that it became possible to make a game that ran on real quantum computers. So that's what I did. And I had a couple of first experiments, which were basically just a random number generator with a story. So I don't count them anymore. And what I would say is the first, really now, the first game for a quantum computer is something that I made called Battleships with Partial Not Gates. And so I'm going to give you the idea behind Battleships with Partial Not Gates now, just so you can see how simple it is. So basically, in a game, things happen. So for example, we might have some sort of enemy, and we might be attacking that enemy. And so we might have to keep track of the amount of damage that enemy has. So we might have a variable called damage, which is going to keep track of how much damage there is. And then we can also have a function, let's call it attack, at least if I can spell correctly. And we will pass to that damage, and then we'll do something to damage. So let's say damage is going to be a variable that goes between 0 and 1. And let's say that these enemies are going to need 3 hits to hit them with in order for them to have full damage and be defeated. So we could have something like this: damage equals damage plus a third every time we attack it. But also we might want to ensure that once we get to full damage, it doesn't go any higher. So we could have something like this. And then this is the basics behind how our, print damage. This is the basics behind how this sort of whole damage mechanic works. So we can look at damage at 0, but then if we apply, I need to return damage. If we apply this function attack, and then we again look at what the damage is, it's still 0. Okay, that's interesting. That's probably because I didn't redo the function. So now it's a third, and then we, also it should be, damage equals attack damage. So damage is 0, we attack, we look at damage again, it's a third, we attack again, we look at the damage, it's 2/3, we attack again, we look at the damage, it's 1. We have defeated our enemy. So this is obviously not a game, but it is something that could happen inside a game. To make a game, you would have to have a lot of other stuff. You'd have to make the pixel for the enemy that's getting attacked. You would have to make the pixel for you. You'd have to work out what this attack look like. You'd have to do a lot of other stuff around this basic little bit. But this basic little bit is implementing the game mechanic of how this enemy gets damaged. Okay, what if we were to make a game that involves something quantum? How would we do this? Well, what we could do is, okay, how is it going to accept our button presses, our inputs? That's going to be done with a classical computer. You are not going to be directly firing microwaves at a superconducting chip in a dilution refrigerator. So you are going to be using a normal controller. So classical computation is going to be handling the inputs. And also, how are you going to see the outputs, where you are not going to be detecting the microwave, or you're not going to be detecting the voltage on a superconducting device. So that is not how you're going to get output. The way you're going to get output is by looking at a screen, and that screen is of course going to be handled by a classical computer. So there's going to be a lot of classical computation going on in any game that involves quantum. It's always going to be a joint operation between classical and quantum. Classical is going to handle the inputs and outputs. It's going to handle a lot of things. So probably you can make everything else classical, but let's replace this little bit, which stores how much damage there is and implements the attack. Let's do this in a quantum way. And why are we going to do it in a quantum way? Not because we think the quantum computer is going to do this particular task better, because, well, this is a pretty easy task to do, so that would be hard to beat, but because we are someone who is, well, either from my perspective, the idea behind making this game was mostly to write a blog post to show people, here are some quantum operations in action. See, it's not mysterious, it's not magical. This is something that you could think about doing as well. So that was my purpose, to educate, and your purpose might be also to educate yourself, to give yourself something to do, some interesting thing to do with anything you've learned. Okay, so how are we going to implement this quantumly? Well, let's use a quantum circuit as something which is going to store and allow us to manipulate the damage. So we set up a quantum circuit object with Qiskit, and we are going to do a 1 qubit quantum circuit, and we're going to extract 1 bit of output from this. So this is how we set up such a quantum circuit. And then we are going to have our attack function again. So we're going to set up a new attack function for this. And this is going to take our circuit, and it's going to do something to the circuit. So what's it going to do to the circuit? Well, it's going to add a gate, which is called Rx pi by 3. So what is Rx pi by 3? Well, you may know, okay, what is a quantum circuit? Let's start a little bit. So let's just set up a quantum circuit called QC, and we can get what's called the counts from this, and you get the counts by running the execute function, which runs the circuit, and we're going to run this circuit on a simulator. So we use air to do that, air.get backend chasm simulator. We're going to use the chasm simulator, and this is one that very much reproduces what goes on inside, so the kind of output you get from a real quantum computer, and we'll do 1,000 samples on it. So we execute it, but the execution gives you a job object, so you don't have to worry too much about that. If you use the result method, it gives you a result object, and from the result object you can get the counts. So you can understand what all this syntax is, or you can just write this line and it will work. So if we now do this, we can look at the counts, and what does the counts tell us? We get the output 0 for 1,000 of these 1,000 shots. But if we were to do a different circuit, if we were to add the X gate on this 1 qubit, giving us this circuit, which just has an X gate, Well, actually, one thing that I've forgotten here is that we also do need to do the measure operation. The measure operation actually looks at qubit, our one qubit, which is labeled qubit 0, and reads out its output and writes the bit that it gets from its output into a bit. So this is now our circuit. And if we run this, then we get the output 1. So if we didn't do this X gate, we would get the output 0. This is just a very simple way of writing a 0. If we did do the X gate, it would flip it to a 1. And what happens when we use this Rx gate is, well, let's use Rx pi by 2. Well, let's use Rx pi. If we use Rx pi, we still have to specify what qubit it's on. Then also we get a 1. So Rx by the angle pi is actually equal to the X gate. If we do X by pi by 2, this is equal to, in some ways you could think of it as half an X gate. It does half the rotation, and you get equally weighted between these two outputs, 0 and 1. And if you do a third, then it's kind of like a third of an X gate. Well, usually we think of it as a cubic root of an X gate, because we usually think of gates as multiplying together rather than adding together. But then you're getting into philosophy. So in our circuit, we are going to add this Rx gate, which does this. And well, that's basically all we're going to do. And we don't actually have to return anything here because it because it just acts on the object. So this is Pythonic stuff. So this is our attack. We set up our object, we attack, and then after we have attacked, then we get a new object. So we get a modified circuit. So we attack. Oh yeah, I didn't put that in here. So we have to specify that we're acting on qubit 2. We attack, and then we can look at our circuit by this qc.draw. But actually we're looking at damage.qc this time. And we have a circuit with an Rx gate in. Okay, what good is that? Well, now we need to actually extract the damage information. And we do that by this process of first measuring the circuit and then running. Well, actually, I'm not going to do first measuring the circuit. In this case, it's better that I set up a new circuit that handles measurement. So I can just stick on the measurement at the end whenever I want. So I'm going to call that measure, and that consists of just a measure gate. And then the circuit I'm going to run is damage QC plus measure. So let's look at that. Okay, it's got our Rx gate from our damage circuit and then a measurement at the end. And then what we want to do is actually run this to get accounts. So instead of looking at it, let's run it. We want damage QC plus measure. We are going to run that circuit. So it's whatever circuit we are using to hold our damage, and then we just add the measurement on the end so that we actually get a result out. And we run that, and we'll get an answer. And in this case, it's mostly 0 with a bit of 1. And this is the effect of the Rx gate. It is, if we had no Rx gate in there, if we hadn't attacked, then we would be fully on 0, no damage. But we did attack, so we're on this instead. So now we're going to define our damage as being the number of samples that came out 1, or actually the fraction of samples that came out 1. So let's print that. In this case, the damage is, well, this number. And then if we were to attack again and do all of this again, the damage would go up. And if we were to attack again and then run it again, the attack would go to 1. So even though it doesn't go a third, 2/3 as before, due to the way that this is being done, it does still implement what we need to implement, which is that when you do it 3 times, you get to a damage of 1. So this means that rather than, because this doesn't just output the damage, we do need to add another function in here. We might call it get damage, which takes this damaged circuit and adds the measurement on the end and runs the quantum circuit. But at the end of all this, we have the same functionality, and then we have to return damage. At the end of all this, we have the same functionality that we had before. We have something which is, so before in the classical case, we just had a variable which held how much damage we had. We just had a function acting on that variable which implemented this game mechanic of attacking. Now we have a quantum circuit which holds the damage. We attack by implementing a quantum gate on that circuit, and we get the information out at the end by running that circuit. So it's all the basic steps that you need in a quantum computation, and it's doing something you don't necessarily need a quantum computer for, but you can use a quantum computer for, so why not? As a simple application of a basic gate and measurement and getting a result out and seeing that you can do these things and that they work, why not? So this is implementing a very basic game mechanic. You would have to write a game around this. And that's what I did in the first game, which is Battleships with Partial Not Gates. It's basically a version of Battleships built around the idea that when you find a ship and you choose to attack it, the way that the attack is implemented is by having a quantum circuit which represents your ships, and by adding gates to that circuit, and then by running that circuit to see if your ships are intact or not. So this is extremely simple, but it is the basis behind this game that I wrote this blog post on, and it got quite a lot of attention just because it was a game that was based on, that used a quantum computer. So even though it was this simple, it caught the imagination of some. Now, of course, now you probably have to do something a little bit more interesting to catch the imagination, but this is the basics behind the game that started it all. So this is probably a good place to see if anyone's got any questions. Now, how do I do that? So maybe I'll stop screen sharing for a moment to see what's going on in the world. And so there's a chat. Anything in the chat? Okay, so people, please mute your mics. I don't think that's for me. So how is the quantum game better than any other game? Well, in general, we will look for tasks in gaming where it's hard to use. Things that are hard to do with a normal computer. And procedural generation, I think, is a good example of this, because you are having to randomly generate content essentially, but you have to make a level that's solvable. You have to make a puzzle that's solvable. You have to make sure that everything fits together well. This is solving complex optimization and constraint satisfaction problems, which a quantum computer would be good at. So if you play procedurally generated games, they're great fun, and I like to play them, but you always see it's not as good as a handmade game. And by using more computational tools, we will be able to improve that. So that is mostly what is important there. Can I post a Git link here? That would be great. Did someone already do that? I'm going to assume they didn't. What is the Git link? Gist.github quantum gym. That's me. Quantum game. And so in case, oh, I should probably have looked. Well, this is the one that goes all of the way. So zoom in on the notebook. Okay, I will do. And so with increasing the shots to a higher value, it wouldn't closely implement the 0 to 1/3 to 2/3 to 1, because actually, well, I think it's getting squared. So probably the numbers you saw are 1/3 squared and 2/3 squared, and it will be a better approximation of those as you increase the shots. And actually, we'll see later something where increasing the shots is something we need to do. Yeah, so the first game, Battleship with Partial Not Gates, was based on a Japanese version of Battleships, where so I think we all know battleships. People place their ships, and they usually go over a few tiles, and you have to try and work out, okay, I've got this one, now which direction I go in. That's most of the fun of battleships. This was one where, based on a Japanese variant, where each ship only actually covers one tile and you just have to hit it a few times. But then I also I did a couple of other versions of battleships, the battleships trilogy, and in one of them I used superposition. But there also, it was again, it wasn't bringing superposition into the gameplay. It was just using superposition to implement the game mechanic. And specifically, I was using Bell's inequalities, which is this test of quantum being truly quantum, and I was just using that so that so there you actually did have a ship that covered two tiles, and you had to hit both of them in order to sink the ship. And the way you found out if the ship was sunk or not was actually by looking at the correlations in entangled states. Yeah, so if you had chosen an equal superposition instead of a rotation, with the damage state of same after attacks, well, yeah, if you made an eigenstate of the X operator, which is the plus state or the minus state, which is I think what you'll be referring to by an equal superposition, with no phases, then yeah, it would be an eigenstate, so it wouldn't get hit. So you could implement that into your game mechanic as well. And is there any reason why we're using a single qubit? Well, we don't need any more. So that's mainly the reason. And it's also just to start off simple, because this was meant as a way of people getting used to the very basics of quantum computing. And the very basics is one qubit. But as I said, I also looked at games which branched out into as many as 2 qubits and even more than that. And a lot of other people who have made games as a way of becoming more familiar with quantum computing have also looked at two qubit. So often people look at 2 qubit mechanics as well, because there's things like Bell's inequalities and Bernstein-Vazirani and stuff that you can start looking into once you get to 2 qubits. So in terms of whether the damage is either 0 or 1, well, the thing is here, I used 1,000 shots. So by doing it 1,000 shots, then you get to do statistics. So if you have 50-50 probability of getting a 0 or a 1, then it means that you get around 500 zeros and 500 ones. So you can look at the statistics of that, and you can say sort of deterministically it's 50-50. If you look at effects where you're only doing one shot, then you will get randomness. So I tend to steer away from randomness because there's this preconceived notion that quantum is just random. So I want to try and use deterministic things as much as possible. There is always a little bit of randomness due to statistical noise, but I try to make it as deterministic as possible to get over these things. So later when we'll look at procedural generation, it will be procedural generation that is deterministic, well, except when it's not, but that would just make a glitch rather than something good. Okay, I have navigated away from that window thinking you can still see me, but no, I have to share my screen again. So let's go back to screen sharing, and let's also, how do we move this widget? Go away widget. Okay. So let me just remind myself what I'm doing. This is the the answers. Okay, yeah. So what we're going to do next is do some more interesting effects of a single qubit, not just these RX gates, but also other rotations as well. And this is a great website you can go to in order to look at a Bloch sphere and see what happens on. Oh, so I should say what a Bloch sphere is in case anyone doesn't know. So the mathematics of a single qubit are, nice and coincidentally, also the mathematics of a point on or inside a sphere. And since spheres are something that we kind of know, it's quite useful to have this visualization. It works for 1 qubit. It doesn't really work beyond 1 qubit. There are ways that you can kind of try and make it work, but it doesn't really. But it's great for 1 qubit. It's great for learning these gates. And I think that even people like me who have done this for many years, when we think about a single qubit, we still think about the Bloch sphere. So it's a very useful tool. So 0 is represented by a state at the top, 1 by a state at the bottom. All of the different types of equal superposition with different phases are represented by the equator. And so when we're doing our Rx, then so this would be the case where we need, well, actually, how many of these do we need to go from 0 to 1? 1, 2, 3, 4, 5, 6, 7, 8. So this is the pi by 8 game, as you can see from here. And so the Rx is rotating around the x-axis. So if we choose a different point for our qubit, we can see that it's rotating around the x-axis. We also have this Ry, which rotates around the y-axis. We also have Rz, which rotates around the z-axis. So these are all of the different kinds of, any gate we can do on a single qubit can be decomposed into these. So this is the way we visualize single qubit states, states and gates. And now I'm going to turn that off because my fan is not liking it. Zoom and that together, not good for my fan. I mean, this is supposed to be a MacBook Pro, and it can't run two things at the same time. Anyway, so what we're going to do next, we're also going to use, we're going to make a game. And for a game, you need a game engine. And a game engine is just something that helps you handle inputs and outputs, basically. Makes it easier to make a game. But we are going to do this inside a Jupyter notebook, because Jupyter notebooks are good for learning about programming. And so therein lies the problem, because you can't, people don't usually make games that run inside Jupyter notebooks. Nobody made Jupyter notebooks to run games, but they did make them with all the kinds of interactivity you need for games. So you can. And so for that reason, I've made a very simple game engine inside Jupyter notebooks. This is not going to rival your Nintendo Switch. It's just for you to use as an educational thing. So the way you can get the game engine is on my GitHub, github.com/quantumgym. It's in a repository called Jupyter Widget Game Engine. And if you look at the gist and you find all of these lines of code, so these are actually bash commands. So these are command line commands. You shouldn't use random command line commands someone's just randomly given you on the internet. I can use them because I trust myself. But I'll just go through what they are in case you want to use them. Git clone basically just downloads everything at this repository. And then this command looks inside this repository to find the file Jupyter Widget engine.py and pulls it out and puts it next to this, next to your Jupyter notebook, which is somewhere you can import it from. And this line also moves another thing that it basically works as a tutorial. And then this deletes the folder that you don't need. So once you've done all that, you have this Jupyter Widget engine.py sitting next to your notebook. Then you can run this import line. So let's go over to where we're actually doing things, and we run this import line, and this will just import the tools that we are going to need in order to do this. And then I can't be bothered to type all this, so I'm just going to bring it over. So this is how you initialize a game, if you are kind enough to call it a game, in this particular Jupyter notebook. Let me even zoom in a little bit more. So basically, it gives you a screen, and your screen is only very few pixels big, in this case 64, and it gives you a controller, which is made up of these buttons here. So it's a very basic game engine, and it's actually based on something called a pew pew. And I meant to have a pew pew with me so I could say, this is a pew pew. Isn't it cool? But basically, it's a games console with an 8x8 pixel screen and a very simple controller, and it's something that you can plug into your computer as a USB device and make very simple games on using Python. So is that me? Is someone writing on my screen again, or is that me? I don't actually use Zoom. We use something far more corporate looking at IBM. So yeah, it's very simple, but it works. You can make games with them. And it's kind of hacky because, as I say, Jupyter notebooks are not made for making games. And it's actually using buttons that you can use as interactivity in a Jupyter notebook and using them to make a game engine. But you basically define it like this. You define how many pixels you want. So I'm using an 8x8 grid. And then you define two functions which act on an input of an engine object. And one is called start and one is called next frame. In this case, I've just put pass in here, which means they're not doing anything. And then you set up the engine object, which you do by calling this Jupyter widget engine and putting in your start function that you've defined, your next frame function, and the screen size you want. And when you do that, it gives you the screen and it gives you the controller, and it also gives you the game that you've defined in these functions. So this function sets up the initial screen, and this function gives you the next frame. And unfortunately, this game engine only allows, doesn't have like 40 frames per second. It only generates the next frame when you press a button. So this function is called whenever you press a button. This function is called when you start. And then you put stuff in there, and that defines your game. So what kind of game we're going to make? Well, we're going to make a walking simulator. And a walking simulator is a game where you just walk around and look at the flowers and think, oh, isn't that pretty? And for this, we're going to define we're going to generate the landscape that we're going to see. So for that, we are going to make a function which for a given coordinate, xy, it returns the kind of terrain that is at that coordinate. So this is a very simple version. So here we have a world which wherever you go, there's grass. We will do it a little bit more fancily later on. So now let's copy all this stuff down again and start incorporating this. So we've defined our get terrain. So in here, when we begin our game, what it's going to do is take this engine object and add the get terrain method as a what do you call it? As the get terrain function as a method, and then it's going to call the next frame. And what next frame is going to do is it's going to loop over all of the pixels. So for x in range L, for y in range L, and then it's going to set the pixel here. So what is this? Engine, if you want to address a pixel, what I think it is, it's engine.screen to get the screen, and then xy to get the pixel at xy, and then something. Well, I made this engine, but I still have to look it up. So what do you do? Okay, so screen has this thing called button style. If you want to change the color, you do it by something called button style. And the reason is that these pixels aren't really pixels of a game engine, because I'm hacking this together. They are buttons. And Jupyter widgets allow you to have a few different styles of buttons. You can have normal buttons, which are gray, success buttons, which are green, information buttons, which are blue, warning buttons, which are orange, and danger buttons, which are red. So we are just using this functionality in order to have colored pixels. So let's say that if a pixel is grass, then it's going to be green. So we go back to our function and we say, okay, let's get the terrain at this particular point, x, y, or let's just call it terrain is equal to engine.getTerrain xy. So we're calling this function at this particular point xy to see what's there. And then if the terrain is grass, then what we're going to do is we're going to make it green, and green is success. So every time, well, when we start, because we're calling it in here, or every time we press a button, It's going to loop through all of the pixels and look at what terrain is there. And if it is grass, it's going to make them green. So let's see what bugs we have. Invalid syntax. Terrain dot blah, 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 blah. So then we look at that for a while and we think about what syntax error we made. And actually, I'm just going to copy and paste it from where I got it right earlier. This is why I have a pre-prepared version. And there you go. We have a screen full of green. We're looking down on the 2D map and it's all green, which is kind of boring. And also nothing quantum is happening so far. So for that reason, we can do something more interesting with get terrain. And maybe I'll just go in here and take what I got earlier and just walk through it with you. So now what get terrain is going to do is it's going to be based on a quantum circuit. So it's going to be based on a quantum circuit because we want to do something quantum. So do we really need to do something quantum in this case? Maybe not, but we want to try out our quantum skills. We want to try out things we've learned about single qubits. We want to try out what we know about these rotations, about the block sphere. So we're going to use a single qubit circuit. And so what we're going to do for this is that we're going to go through basically what we did before. We're going to add a gate to our circuit, and then we are going to add a measurement to our gate. We'll just do it directly this time. And then we are going to run it. So this is the same as before. We use this execute function, we put in our circuit, we run it on the simulator, we use 1,000 shots, we get the result object, we get the counts, and that's our counts. And then we're going to take this and, well, before we took the counts for the output of 1 and divide it by 1,000 to get the damage. So if this was between 0 and 1. In this case, we'll call the damage P. It's not damage anymore, so let's call it P because it's the probability of getting a 1. And rather than just having this line, we should account for the fact that sometimes, if it always comes out 0, this counts dictionary will not have a 1 entry, and then it will give us an error if we ask for the 1 entry. So we can say, well, if there is a 1 entry in counts, then do this. If there's not, then it's just P equals 0. So that's just Pythonic cleaning up. And then we have a value, this value P. And we can use that to decide what the terrain is. So let's think of this P as basically being the height. In fact, why do we call it P? If it's a height, let's call it H. And then we can say, well, okay, well, if the height is less than a certain value, then we'll say that's C. If it's less than a slightly larger value, then we'll say that it's sand. Otherwise, we'll say that it's grass. So we're going to get some C, we're going to get some sand, we're going to get some grass. And then we have to come here and start doing, adding to our game engine the ability to have things other than grass. So else if, okay, a better way to do this is the way we did it before, but then the way that we did it before gave us an error, so maybe it wasn't as good as all that. Let's try again. So we'll get that, we'll call it terrain, and then we'll start putting terrain in all of these. Otherwise, it recalculates it every time, which makes it take longer than it actually has to. So if terrain is grass, then it's success. If terrain is sand, then it's whatever sand is, and otherwise it's the thing for C. And I know that blue is info. So then I just have to look up what's it's orange, warning, of course. This is just arbitrary stuff because I'm hacking together a game engine about something that shouldn't really be a game engine. So here it's still, I don't think I executed my new function, so it's just doing the grass function from before. And now we get something more interesting. We've got some C, we've got some sand, we've got some grass. But actually I skipped over the whole what is in my function. So here I'm just doing a rotation around the x-axis by an angle that depends on x and y. And I've chosen this to be what I've chosen fairly arbitrarily for this to be x plus y times pi divided by 16. So why have I chosen this? Well, in a map, you typically expect one position to be the same terrain as the next. Sometimes it's going to change, but mostly it's not. So we want whatever terrain is here to be the same as, or most likely the same as whatever terrain is here. And it's based on the probability of us getting a 1. And the probability of this getting a 1 is based on how much we rotate around the block sphere. So basically, if we just only rotate a little bit between two different neighboring points, then most likely they're going to be the same thing. So that's basically what we do here. We turn the coordinates into the angle of rotation such that for two neighboring coordinates, ones that differ only by 1, for x or y, then the angle of difference here is quite small, and therefore when we measure it, the difference in h will be quite small, and therefore most likely they end up the same terrain, although sometimes, of course, you'll cross a boundary. So this is what we're seeing here. We're seeing the terrain that we get from this particular function. And it's kind of arbitrarily chosen. We could have done some other things. We can add other gates here. Maybe let's do a rotation around the y-axis. But instead of x plus y, we do x minus y. And then what landscape does that give us? It gives us something a bit different. And then we can experiment with different things to get different sort of landscapes. And of course, it's just very zoomed in because you're only seeing an 8 by 8 little section. You also want to know what is going on in the rest of the map. And also some people who have experimented with this themselves have made multiple processes here. So you might want to add little ripples on the water, and you can do that by having a whole other process which adds ripples on the water or flowers in the grass or whatever is going on here. So far though, we haven't got a player. So let's add a player. Let's have player X and player Y as things which determine where the player is, and we'll start it off at the position 4, 4. And then we can have something where we say, well, we want at the player's location, P underscore X, P underscore Y, to have a pixel of a different type in order to show that the player's there. So let's use red. And okay, px is not defined because I have not set it as, it's not in scope. It's a Pythonic thing. So we'll set it as an attribute of our engine, and then it won't complain. Or it shouldn't complain anyway. So let's run that now. And there we have our player sitting there. But we want to be able to move around. So we're going to have to update the player's position. And for that, we have this whole sort of functionality that you can find in the documentation for the game engine. When you press the up button, then it will call next frame, and it will call next frame such that this thing, engine.controller_up.value, is true. So if you want to detect pressing up, you do this, and then we can use this to make our player go up. So let's run it now, and if we press up, our player goes up, which is nice. And if we press down, well, nothing happens because we haven't told it to do that. But if we do tell it to do it, then in that case, we'll be adding 1 rather than minusing 1 from the player's y coordinate. And rather than bother with typing in the next two, I'll just steal them from the one that I made earlier. And now we have the ability to move around. We can walk around this landscape we made. And let's walk off the screen. And then we get an error because, well, it attempts to write to a pixel that doesn't exist. So then we have to deal with this. Okay, we don't want it actually to write to the pixel here. We want to do it mod the size of our screen. And then this won't happen anymore. So let's run it now. If we move, it comes back the other side, but that's not really what we want either. We want to explore the rest of this world. So for that, we can have the notion of screen. So we're moving on to a different screen. So we can say that the screen, the X, and we can have the X and Y coordinates of the screen to be the floor. So that means rounding down when we take the player or engine dot px and divide by L, and the same thing with Y. So then we start off with screen coordinate 0, 0, but if we move off that screen, then we'll get a new screen coordinate. And then we have to take this into account when we ask for the terrain, because we're not actually asking for X, Y. We're also asking, well, on the screen with this particular, well, this is all classical stuff, so let's not go for it too much. But if you think about it, if you move to if this is called screen 0, 0, and you move to the next screen, and that's called screen 1, 0, and you want to know what the coordinates are in that screen, then they're basically the screen you're on, the coordinates of the screen you're on, times by the width of the screen, plus the coordinates within the screen. So I think that's everything. So we run that, and now if we move off the screen, then okay, it didn't work. Terrain is blah 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 blah. Yeah, something's wrong. Something is wrong, and to be honest, it doesn't really matter too much, does it? So I'm not quite sure why it's not working. Let's try it again. We move off the screen and we want to get the next screen. Okay, it updates. Now we're on the next screen. We've got another little bit of grass and sand. We move down here and we find the next screen. Okay. It's not fully working for some reason, but you get the idea. You move around between screens and you can explore this map. And you might notice also as I'm moving, things are changing a little bit. And that's because it's taking a little bit of time. That's because it's redrawing the whole screen every time. It's going through each of these pixels and running a circuit every time I move. And when you are near the boundary, statistical fluctuations mean that it might be random whether you decide whether this is sea or sand. Really, you wouldn't want to do that. You would want to write the whole screen and not recalculate these things until you move on. So this is something you can do if you want to improve this. You can also make it actually a more interesting map that you're walking around. You can make it so you actually interact with things. Like here, if I walk into the sea, then I can perfectly happily walk around the sea. You shouldn't really be able to do that. Maybe you want to have a boundary there. But this is just the beginning of how you might explore your knowledge of single qubits to do something interesting, which is creating a map that you can actually walk around. As a demonstration of the fact that we can use games made with quantum computers as a way of exploring information exploring what we are learning about quantum computers. But it's also an example of procedural generation, because this sort of task is done in games where you have a function which you give it some coordinates and it will tell you what is there. So for example, in Minecraft, you would have this as you walk around. Minecraft doesn't decide what is absolutely everywhere before you even begin. But as you start walking, it will decide, okay, well, he's starting to look at coordinates X, Y now, so let's look up what should be there by some sort of algorithm, exactly as we're doing here. The difference is that you would be, well, for one thing, this is a much simpler algorithm because we're just using it as a way of applying knowledge about quantum computing. But if you scale this up to many qubits, you introduce ideas of optimization, of interference, of entanglement, then you might actually come up with a procedural generation algorithm which does do something that normal computers couldn't do. So in new forms of procedural generation. So this is basically me live coding a very simple game. And now I'll see if people have asked any question. So if people, okay, I can't import one of the modules. I should have said if you run the bash commands in the notebook and it makes the file next to your notebook, well, your notebook has probably already, as you turned it on, looked at what files were near it and not seen it because it wasn't there yet. So if you just rerun the notebook from the beginning, restart the notebook, then it will look again and see it, and then you can do it. But you can also just download it manually. But again, you probably have to restart the notebook. Yeah, so the Jupyter widget engine, yeah, it's not part of Python. It's something that to say it was written is charitable, hacked together, I think. Yeah, but so if you just rerun the notebook, that will probably fix your problem. But also, this is probably something that you want to do in your own time as well, rather than while I'm doing it. So that is the basics of what I wanted to run through. There's other things that I could talk about as well. What am I doing? How do you make Zoom? Where did Zoom go? Zoom, come back. So if I share screen, one other thing that I can point out is, okay, so this is the Jupyter widget game. And also, if you go to the Qiskit textbook, you have another example of a game that exists within a Jupyter notebook. So this is this Hello Qiskit game that you can see here. And let's actually try working it out. So this runs within the browser. So if you run this cell, it will do what's written in the cell, which in this case is just saying hello world. But so this is mostly so you can see that the kernel takes a while. I have a version locally so you can see what's going on. And then you have to set up some stuff, blah, 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 get on with it. And then it's basically a set of puzzles, which again are using features within the Jupyter notebooks. It visualizes 2-qubit states, and then you can apply gates to that. And it goes through and teaches you basically a lot of stuff about 2-qubit gates using this very simple realization, this very simple visualization. Sorry. So there are a lot of things before you even get to the quantum. Come on, quantum. So you can look through these puzzles and learn about quantum computing in these. So it's giving you the gates that you're applying, and it's giving you this sort of visualized way of looking at them and thinking about the gates. But also, if you want to make a game with a quantum computer, the way you make these puzzles is just through these lines of code. This is how you initialize what the state looks like, what the target state is that you have to reach at the end, what gates you're allowed, certain details about the visualizations, and then you run this, and that is what runs the puzzle. So another way you can learn about quantum computing through games is to use these puzzles that are in the Qiskit textbook, and to learn about it through these puzzles, but also to make your own puzzles. You can come in here, and there's a tutorial in how you make these puzzles for yourself. So this is another way that you can learn about quantum computing. And I could go through all of these. I could do a live stream of me playing my own game. But actually, there's quite a few puzzles in here, so you're probably better doing that in your own time. So this is a Jupyter notebook that is, as I said, on the Qiskit, the Qiskit textbook. So you can come here and use it. But also there is an app version. It's called Hello Quantum, and you can, well, there was something we had to update to keep it recently, and I think we updated that. So I think it should still be on the app and Play stores. And of course, it's something that we provide as an educational tool, so it is free, just as a Qiskit textbook is. So that's another aspect of quantum with games. And then I suppose the only other thing that I wanted to say to you is that I have a Twitter link so this pinned tweet in my Twitter, which is twitter.com/dikadoku, is a whole bunch of stuff that you can use as resources if you're making your own game. So it starts with this article that I mentioned earlier, which just explains the history and the scope. And then it tells you about the fact that you can use these Hello Qiskit puzzles. And then it also talks about this Jupyter widget game engine. So this is actually like a very simple 3D game I managed to make in the game engine back when I only had 2 buttons. And but of course, most people will aspire, as I say in this particular tweet, in this thread, to fancier games than you can provide with Jupyter widgets like Hello Quantum or this Jupyter widget game engine. So, but the trouble with this is that it's hard to make games with Python, basically. Or at least it's hard to make games that it's easier to share with people, and people usually want to share games. So there were workarounds for this. And one workaround is something I've made called micro Qiskit, which is basically just Qiskit, but in a much easier form. And this has been ported to various languages. So, for example, this very same terrain generation that I've just showed you, I implemented on a game engine called the Pico 8, which is a great game engine for making sort of retro-looking games. And I made this with as just a very simple prototype with my daughter one day. So this is my daughter as a princess with butterfly wings in this particular game. So this is also something you can use. You can make games in the Pico 8 using micro Qiskit, and you can find the links all in there. And yeah, so that is basically the 2 notifications have just popped up as we've been on here. I'm thinking two people from this call might have just followed me. Yeah, so this is the end of my information dump, basically. So yeah, where is this book? Someone provides a link to the book. Excellent. So is there anything else? Well, that's basically all that I plan to share with you, but I can answer more questions. So who wants to ask what? And so have I used any of these things that are competitors to the company that I work for? Well, I'll let you in on a little secret. The first game ever made for a quantum computer ran on IBM hardware, but it used Project Q. And that was because Qiskit didn't exist yet. As soon as Qiskit existed and was the best way to actually use real hardware, I switched over, even though I didn't work for IBM at the time. So does IBM have a distributed quantum computer? Well, it has what it has. And so usually we have multiple devices online. Each are prototype devices of a few qubits, and you send a job, and you have to wait in the queue, and it comes back. So it's a fairly simple workflow. Should the Jupyter widget engine be an IPYNB instead of a PY? There is an IPYNB which acts as the tutorial, but the actual tools are in the PY. So you should be importing. So you should have the PY somewhere, and you should be importing from the PY. You can also open the PY, even on GitHub, and just copy paste all of that stuff and paste it into a cell of your Jupyter notebook. And then you'll have one huge cell, but you'll have it. It'll be the same as importing it. So computer graphics. What are your thoughts on the potential for quantum computing to impact the world of computer graphics? I know this is something that people have looked into. There are papers on it. There are people that have tried using D-Wave to do it. To be honest, myself, I don't think it's hard to imagine using quantum computers within the game loop. So the game loop is when in the case of this particular game engine, it's when you call this next frame. And all game engines have something along those lines where you call a function which looks to see what will happen in the next frame. And typically you're running that for 40 FPS, you're running that 40 times a second. For 60 FPS, you're running it 60 times a second. You're running this very quickly. And so if you're having quantum processes in that game loop, then you have to have them run very quickly. And at the moment, if you run a process on a real device, you have to wait at least a minute to get the results back. So it's not really feasible to have it in the game loop. Now, in this example, I did have it in the game loop because this is kind of a proof of principle thing. But if you're looking for real applications in gaming, I think personally, the most reasonable ones are not to have it in the game loop, which means, unfortunately, not using it for rendering. But if we see the expansion of what we've seen recently of games going on the cloud, well, quantum computers will always be on the cloud. So maybe there is scope for having quantum in the game loop at some point, but not today and not tomorrow. So that's not, so it might be, it's worth looking into, but it's as something for the long term, but not in the near term. Someone's posted a link to Hello Quantum. Excellent. What game projects are you working on? That's a good question. So there's this thing. So yeah, one thing I've been looking. So there's why is it taking me to commit? So there's this thing called Q of Rye, and does GitHub just changed the way it does things? I don't like it. Well, no one ever likes change, do they? And when technology companies change how things look, you always think, oh, this is horrible. Well, I'm sure it's fine. Okay, so there's a paper in here, and I've tried to make it fairly accessible. And this is something I've done, which is, it runs on a real device. It runs on the 53 qubit device that we have. So this is our 53 qubit device. It's called Rochester. And I'm basically looking into the idea of using this as a rudimentary AI for a game like Civilization, where you have different countries, and these countries are trying to make decisions on whether they should attack or defend or whatever. And basically, I'm using each qubit as the rudimentary AI for one country, and the device as a whole and the correlations between these are dictating the kind of diplomacy that's going on. So you're manipulating these qubit states in a way that kind of, so like the 0 state, I can't remember exactly how I encoded it, but maybe the 0 state is a state of maximum defensiveness. So if your country gets attacked too much, then you rotate towards the 0 state. And things like that in order to implement a rudimentary AI. With the kind of same sort of way of thinking about things as we do when we use quantum computers to simulate things. Because simulation is something that's kind of a good thing to do on near-term devices. So this is a procedural generation project I've been looking into, and it's something that I was able to write a paper for. So it's got graphs and everything. And here is the evolution of the borders of these nation states as time goes on. So again, it's maps, but instead of being 1 qubit maps, as in the example I went through today, this is 53 qubit maps to simulate the geopolitics of 53 different nations. So you can check that out. And oh, yeah, I think I completely forgot that I am not sharing my screen anymore, am I? So I will just share the screen. And basically I'm here at this, so I was complaining about how GitHub looks now, and none of you could see this new GitHub. Maybe that's for the best, eh? So yeah, 53 qubit device, simulating the dynamics, the geopolitical dynamics of some nations to make these borders of nation states. Graphs, paper, this is something you can look into. But also the tools behind this are something I call quantum graph. So let's see if we can find that easily. And so if you want to use basically the thing that I used to make this, then you can go to this quantum graph, and it's something that's freely available online. Actually, maybe you should go to this version so the clicks get in the right place. It's something that's freely available online. It might take you a little while to work out what you might want to do with it, but it's basically using some of the same. So, well, read the paper and it will give you a bit more of a tutorial than this does. But this is something you could also use to come up with your own many qubit procedural generation project. Okay, so let's stop sharing and I'll put in here the link to that. What else? So computer graphics, what am I working on? Oh yeah, a short question that I answered very much. Is this session recorded? Hopefully. Does Qiskit exist in other languages than Python? The answer is no. And yeah, the answer is mostly no. So there were some early attempts to put it into other languages that you'll find traces of if you dig far enough, but they're not really compatible, I think, with the existing version anymore. But micro Qiskit is something that we've made basically to be easily portable. So Qiskit is this huge, is the biggest and most advanced framework for quantum computing, which is great because it means it's big and advanced, but also it means it's hard to port. So micro Qiskit is then made to be the smallest and least advanced framework for quantum computing. It's basically 100 lines of Python. But it has all of the basic functionality of setting up a circuit, adding gates, and running it. This has been ported to other languages. I think if you look at, if you search for micro Qiskit, well, I'll tell you where it is. It's github.com. Everything's on GitHub /Qiskit-community micro Qiskit. So this is something that has been ported to Python. So it's been ported to Python, even though it's already Python. So that means it's ported to Python 2 and MicroPython. It's been ported to Lua. It's been ported to C++. It's also been ported to a couple of other things, but we haven't put them in the repository yet. And also, if you have a language that you want to use, then you can kind of look into making your own MicroPython port and share it with us. So really, we want people to be in the Python ecosystem, but as a way to allow people to try it in their own favorite language, then you can use micro Qiskit. Yeah, so you pasted the whole thing and it worked. Cool. You have a big ugly cell, but it works. So how is IBM handling error correction? Or can you share your screen from Amir? Yeah, thanks. As soon as, so I didn't read your thing, but somehow it telepathically got to me. How is IBM handling error correction? Is there any latest publications on it? Well, yeah, it's a good question. That's a good question. We're handling it. We're handling error correction. So we have plans to do error correction. Our plan is always to have hardware that is compatible with the needs of large-scale error correction. But also, there has to be a bit of a give and take here. So if you're an error correction researcher that is purely theoretical, then people come up with these nice three-dimensional error correcting codes or four-dimensional error correcting codes that need to be embedded in four-dimensional space and say, look, this is a great error correcting code. It's like, yeah, it's not really physically feasible, though, is it? So there has to be a lot of a dialogue now as we come closer to the realization of the technology, a dialogue between people making the hardware and people doing error correction to make sure that we come up with the best middle point, compromise between the two. I'm sitting in Switzerland, I should know the word compromise. Yeah, so we're working towards that, working to make the best hardware and work out ways to do error correction that is tailored towards it. But what I am doing more specifically in my own error correction work is using small-scale examples of error correction as tests of the devices. So I run repetition codes, which are not good for quantum error correction in general, but do have all of the basic principles. I run those on the devices we have at the moment to see if the graphs we get, the results we get, are the results we want to get, or they're something completely horrible and crazy. So if you look at the repetition code section in the Qiskit textbook, you can learn more about that. And I will actually update it in the next few days. So if you really do want to read that, then I would probably suggest you read it on Friday instead of today. Yeah, so that was me. If I want to learn how to create quantum algorithms at a university, which one would I recommend? This is always a very hard question. The easiest thing to say is don't look at league tables of how good universities are, because that's irrelevant. Think about exactly what interests you, what kind of algorithms, what kind of approaches interest you. Look for the people who do that, because it's the people is always the people is who you work with. The people, when you go to conferences and someone says, what are you doing? Who do you work? Where do you work? They always care about who you're working with rather than where geographically. So look at who is doing what and see who you align best with. Is the 53 quantum computer available over the cloud on the Quantum Experience? Okay, it is for me because I work for IBM. It isn't for most people. So you have up to a 16 qubit device that is available publicly. To be honest, I only use the 53 qubit to show off. The 16 also runs. We want Perl. Well, you can port it to Perl. I don't think anyone's ported it to Perl yet. As long as it has classes, it should be fairly easy. If it doesn't have classes, micro Qiskit, really cool. Thank you, Amir. Increasing the coherence time is a great way to reduce error, but you can't. So basically, we want to have as few errors as we can. Always the best way to deal with errors is to have as few errors as we can, but we can never reduce that down to 0, and that's why error correction is required. So where are we hitting limits that quantum computing is promising to solve? Well, it's kind of hard to say, because people who make games, people who do procedural generation, they're very clever people. They know the tools that they have available to them, and they use them as best they can. You don't usually get to a point where people hit a problem and then they go and complain about it on the internet. Oh, I wish the computational complexity of this particular thing was less, and because it's not, then my whole game is going to be a failure. They just find another way to try and do it. And by coming up with new methods, both classically and quantumly, people get new ways of doing things. So we're just going to enrich procedural generation by bringing new techniques. It's not that people are waiting in a queue at the moment for certain problems to be solved, and that we're going to solve them. For a company who's focused on hardware without a software framework, would you recommend to partner with an existing one like IBM? Yes, of course. What would be the advantage? It's awesome. And disadvantage? Oh, you're asking the hard questions now. So, of course, Qiskit is an open source project. Anyone can contribute, but most of the people who contribute are people who are paid to contribute by IBM. And of course, that means that a lot of their thinking is geared towards the particular hardware of IBM. So a lot of the transpilation, which is how you take a circuit and turn it into something that can actually run, a lot of that is done with the needs of superconducting qubits in mind. So that is something that you might have to think about a little bit yourself, even if you are using Qiskit. But also a lot of that transpilation is something that will carry over. So it was done with superconducting qubits in mind, but it will still be good for other hardware. But other than that, things like making circuit objects and adding gates, then there's no need to redo all of this stuff every time. So I think plugging into Qiskit is a good thing. And a few chapter ion groups and spin qubit groups have written backends for Qiskit so that you can also use their hardware. Is it possible to seriously get into quantum computing without formally studying physics, just maths and CS? Absolutely. This is not just now. Like now we've got things on the cloud, blah, 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 everything's awesome. But even back in the past, quantum information and quantum computation was always a very multidisciplinary endeavor. So you had people who were doing quantum computing PhDs in maths departments who had a maths background and who hadn't done physics for years, or in computer science. So we've always been maths, computer science, and physics brought together, and there's been people doing their studies in these different areas. And even as a computer science, as a physics person doing quantum computing in physics departments, I was always viewed as the crazy weirdo. He's not really a physicist. He's one of those quantum computing guys. So yeah, don't feel you need to do physics. Formally study physics. You will need to know some physics. How did I come to IBM? Well, yeah, how did I come to IBM? So through games, actually. So yeah, I did a PhD in Leeds on quantum error correction. I moved then here to Basel, where I still live, to the University of Basel to do more research on quantum error correction. And then at some point in 2015, it seemed like quantum computing was so far away, such a sci-fi thing, that I thought, well, my research is not really impacting the public. So I wanted to make a citizen science game, which is called Decodoku, and I think you could still probably download it. But I don't do any upkeep on it at all. So if it's disappeared off the App Store, then I wouldn't be surprised. But it's called Decodoku, and so it's a citizen science game, a game you play to learn it, to contribute to error correction. And then that was 2016 that I put that online, and that was the same year that IBM put their devices on the cloud for the first time, which meant that while I was in this mode of outreach and teaching people, suddenly we actually had the hardware, this thing that seemed so far away. We had the hardware publicly available. So I started using the hardware a lot and talking about it and writing blog posts and writing papers and making the first game. And these activities made me, put me on the radar of international business machines. So yeah, then it was inevitable that we would collide at some point. So my qualifications are, I have a PhD. I come the boring academic route. What is the single most important differentiator to doing work with classical computing? Well, really, you work at the machine code level. If you look in the Qiskit textbook, the first chapter is how to add, and not just how to add on a quantum computer, just how to add, the concept of adding, and also how to do it in the machine code level that we use for quantum computing. So it's mostly in classical computing, we're used to high level stuff. So adding is easy on a classical computer, but a quantum computer, you kind of have to think about all of the bits involved. So I think that's the most important differentiator, to just think down at the machine code levels. What are the current hot problems that we're trying to solve? Well, mostly to get quantum computers that can do useful things for people. We've got prototype devices at the moment, but of course we have to develop the technology more in order to get fault-tolerant quantum computers, and then we can run all the textbook algorithms, and then it'll be awesome. But also, as much as we can, try to make algorithms that are suitable for the current era, the era that's just beginning, which we call a NISQ era. Oh no, some people call it the NISQ era. We call it something else. But basically, the near-term era, where we have devices that are near fault-tolerant. We're trying to work out as fast as possible how to give people results that they wouldn't have had otherwise. So what are the current hot problems? Oh, that's the same one. What are some of the general expectations of someone applying to IBM for a quantum computing job? I don't know how to answer that really. There's so many different kinds of people with different kinds of background that are working on quantum computing at IBM at the moment. So passion, let's say that. That's the most important thing. Is it possible to get a job in IBM quantum domain without having a PhD? Yes. Typically, you wouldn't be working on the science without a PhD. Like, I work for IBM Research, so this is the research division of IBM. Well, even there, you can get a job without a PhD. So yes, and so a PhD is still a good thing to have. It opens more doors to you, but the doors are not closed otherwise. And maybe take one more question so we can end on time. yeah, is QC just hype, or will it be useful? I hope it will be useful. I think that's probably, I'll end on that one. As long as quantum physics behaves the way we think it does, then quantum computing will be useful. And if quantum physics doesn't behave the way we think it does, well, that would be even more interesting in some ways. So cool stuff is coming, whichever way it goes. But I think we know what we're doing. Okay, so that's all, and we've ended a little bit over time, but yeah.
Yeah, thank you everyone for coming. If any of you didn't have a chance to get your questions answered, you can forward it to us and we can try to get it to James so he can answer it there, or maybe you can reach out to him directly if you want to say your email or some way to contact you. Yeah.
Well, so Twitter is probably the way. And the Qiskit Slack, so if you go to qiskit.org, you should be able to find a way onto the Slack. And the Slack, well, either I will answer your question or one of the many other people in the Qiskit community will.
Yeah. So we will reach out to you in a couple of days, all of you, and we'll send you the recording, and you can reach out to James with any further questions. But thank you all for coming and attending this. Bye.
Yeah, thanks.